As a professional in the roofing industry, you're well aware that any time roofing granules are moved or poured or transported, segregation of the granules into fractions of similarly sized particles will occur. How severe the segregation is and the adverse effects on your business depends to a large extent on the care you take in following a few well-established rules in materials handling.
Today, we're going to look first at the specific causes of granule segregation. You'll recognize many of these from your own operations. Then we'll examine several techniques for preventing or minimizing these effects. We'll be using a variety of equipment to demonstrate both the causes and the cures for segregation. In spite of the wide size differences you'll note between this equipment and your own handling systems, the results are the same. For these demonstrations, we'll be using a mixture of two different size 3M granules. We've color-coded the sizes so that you can easily see what happens. In mixtures of the same color, segregation is often difficult to recognize until it's too late. These red granules are plus 16 mesh size and are somewhat rounded, while the white granules are minus 16 mesh and are more flat and elongated. We've blended these granules in a 50-50 mixture. All our tests today will use this formula. One of the places segregation will always occur is when the particles are discharged through a small opening and allowed to form a cone. Watch what happens. As the cone forms, you can see the edge effects starting to show. The larger red granules are separating to the outer edges of the cone. We've located the cone against the side of the box to provide a better look at the inner structure of the cone. You can see that the finer fractions have started to segregate at the center of the cone. This is caused partially by the fact that the larger particles will roll further than the smaller ones. There are three reasons that the larger particles accumulate on the outside of the pile. First, they are more rounded than the fines, so they roll instead of slide. This rolling action causes a slightly shallower angle of repose for the large red particles. Second, the smaller particles tend to fall between the cracks of the large particles in the pile. Third, the larger particles have more inertia than the small particles, so they roll farther from the initial impact point. Anytime you allow a mixture of sizes to form a cone, you'll get some degree of segregation. You can see the effects of this kind of segregating movement when you look at a cross-section of a model silo which has been center charged. Let's charge this silo a couple of more times. You can see the segregation continuing to form, with the larger granules moving to the outside. Let's follow our typical example one more step and empty this silo from the bottom. You'll note that it has a funnel flow outlet with the sides at about a 40-degree angle. Fairly standard around the industry. Watch what happens when we discharge this silo. We'll screen each load as it comes out of the silo and place the separated fractions in these columns to measure the segregation exactly. During the first load, flow appears to be normal. As the second load starts to move, notice the channel of flow that is starting to establish itself down the middle of the silo. As the third load moves out, notice that the material at the edges moves last, if it moves at all. As the inverted cone begins to form at the top, the larger particles, which are faster than the smaller ones, move down the slope of the cone sooner and eventually form a darker stripe down the center of the flow channel. Are the loads we're pulling out at the bottom still within the specifications we started with? By screening each discharge load, we can see that the first sample was pretty close to the starting percentage. but it didn't take long for the naturally occurring segregation to become apparent. Here's a fairly common silo design, which many of you know can cause segregation. Charging is from the side, while discharge is from the same side. The larger red particles have collected on the side opposite the charging chute because of their tendency to roll further. Anytime we discharge from the same side as we charge from, we're going to get a lot of segregated fines for most of the early discharge. This is another example of storage silo design. Side charging from the top with 2 funnel outlets at the bottom. You might think this would prevent segregation to a degree, but let's watch to see what occurs during charging. Initially, this design doesn't look too bad until both funnels at the bottom fill up. Then a really long slope starts to develop and segregation of the larger granules starts becoming very noticeable. Discharging will produce loads both in and out of your specifications. Segregation occurs anytime you allow a mixture to flow freely down a pipe or a chute. In an arrangement like this, you allow the individual particles to slide on the chute surface. That gives the large, less frictional granules a chance to move further. Let's take a look. As the granules move freely down the chute, some of the larger ones outrun the smaller ones, again creating segregation in the pile at the bottom. We can measure the difference in the angle at which each sample will start to slide down the ramp. There go the larger granules first. The sample of the smaller granules follows soon after. We call the angle of the slope at which the material will remain stable the angle of slide. The difference between the two angles is small, but it's enough to cause the larger granules to flow down a slope faster. Okay, let's look at the causes of segregation as we've seen them so far. First, segregation will occur whenever particles are allowed to form a cone. Funnel flow hoppers with a shallow angle will cause flow only directly above the outlet. This often causes sequential emptying of fines, then coarse particles. In addition, segregation will occur anytime you permit granules to slide freely down a chute. If you're seeing a segregation problem, it's very likely caused by one of the factors or a combination of them. Now, let's look at some cures for segregation. You may be surprised at the variety of options available to you. Each one is designed to modify the flow patterns you've seen up till now. flow patterns that may very well be causing you problems right now in your installation. For example, the charge point for this silo model was on the same side as the discharge. By moving the charge point opposite the discharge, segregation still occurs, but we reduce the segregation effects during discharge, especially in a shorter silo. Now, the first load out will be heavy in coarse material, but the succeeding loads will be uniform. This technique may be economical, but it is not ideal. In this example, the silo is center charged and center discharged, so segregation occurs from the cone formed in the center and from the flow channel which develops upon discharge. One cure here is to move the charging inlet to the edge. You'll see a limited amount of segregation forming due to the slope. However, on discharge, the central outlet draws both from the high fines and high coarse areas. The contents will tend to remix, and segregation will be minimal, as you can see from these samples we just drew and screened. We realize that changing the location of the inlet and outlet on an existing installation could be impractical for a variety of reasons. So here's another approach you could use. In a round silo or hopper, the insertion of a conical baffle and deflectors under the top center inlet will provide several interesting changes to the segregation resulting from the flow pattern. Watch what happens as we charge this modified vessel. Notice that we're now forming two piles instead of one, and that the pattern of segregation is much less obvious. There is some segregation of fines here and here. This will tend to be remixed by normal funnel flow at discharge. Another remedy is to alter the angle of the sides of the funnel. This little device will graphically demonstrate the advantage of mass flow through a steeply sloped funnel. Notice that all of the flow takes place down the center of the funnel, while none occurs down the side. This discharges the fines first. A well-mixed load will begin to segregate just by moving it through this shallow funnel. A load already segregated will just be made worse. Now, watch the effect of a steeper funnel angle, somewhere in the range of 60 to 70 degrees. You can see that the sides and the center are moving at nearly the same rate. A steeper angle to the sides of the funnel can virtually eliminate the segregation that you saw earlier. We call this mass flow, as opposed to the funnel flow you saw earlier. If changing the angle of the sides of the flow seem too costly or impractical, here's another modification that can have a large impact. It's called cone in a cone. This is another arrangement to alter the segregating flow which occurs in a shallow funnel. In many existing installations, this could be a bin insert. By mounting a second cone inside the first one, the mass flow characteristics are returned to the material, and segregation is greatly reduced as the speed of the outer and inner flows are matched. Segregation occurs anytime you allow a mixture to flow freely down a pipe or a chute. Here's a fairly typical arrangement seen in a lot of granule handling installations. a chute feeding onto a moving belt. The correction here takes two forms: a much steeper slope on the chute and the choke feed system at the end of it. While filling the chute, some segregation will occur with some larger particles on top of the fines. This, however, corrects itself fairly rapidly as the material is allowed to flow onto the belt. Notice the vertical drop at the end of the chute, which helps maintain the choke feed. Notice that there are more larger particles on the side of the belt away from the chute. That's because of the slope established in the tube during charging. However, the choke feeding prevents the larger particles from outracing the smaller ones as they come down the chute. As the flow in the chute progresses, notice that the segregation gradually disappears, and the blend on the belt is now very close to what it was up in the hopper feeding this system. The tendency to segregate has been sidestepped by altering the flow patterns. Throughout these demonstrations, we've talked mostly about preventing segregation in materials that are evenly blended to start with. But what about material that starts out somewhat segregated? Is there anything you can do to remix these materials? Yes, there is. The results of this next demonstration may seem unbelievable, but there is no trickery here. These three sharply angled funnels are mounted offset to each other. This would be a good method of remixing material while recharging bins above the line. Watch what happens when we charge this funnel system with material that is as sharply segregated as you can get. We charge the top funnel with the red and the white granules in equal proportions. Notice at the bottom that the only segregation still remaining is that caused by the fact that we're allowing the material to form a cone. The triple funnel arrangement has effectively remixed the segregated granules. Let's do that one more time. That's one example of an arrangement which will effectively remix segregated material. Here is another. We've installed a cone-in-cone structure in the frontal throat at the bottom and a series of graduated cylinders in the body of the hopper, reducing in size going upward. This sort of arrangement would be excellent to assure blending from several different loads or to remix previously separated material. What we'll do is provide a mechanism to change the velocity profile of the material at the sides and at the center of the hopper. These two flow rates need to be more closely matched. As you can see, we made this particular test as difficult as possible. I'll mark the top of the load for reference later. Now, watch the results. Notice that the first discharge is still totally segregated, which is to be expected since the action and the interior cylinders has not had a chance to take over. This early part of the load would be mixed back into the hopper. In normal operations, you'd never see segregation of this magnitude. Now, the desegregating action is beginning to show, but it's not yet perfect. Notice that the top of the load inside the hopper has formed an inverted cone, indicating movement in the center, and that the material at the sides is moving also. This illustrates that the outer and inner flows are starting to match. At this point, it's apparent that the material is now mixed in about the same proportions as the original charge. If the material had been only slightly segregated at the beginning, this degree of mixing would have occurred earlier. By measuring the distance from the mark I put at the top of the load when we started, we can see that it took about 5% of the load to start achieving a complete mix. The unloading will continue at this level of mix until the very last amount comes through. If we add more to the hopper, effective mixing will continue. Let me briefly review what we've seen here. Granules of different sizes will separate under certain very predictable conditions, such as being allowed to form a cone or a slope or in free-flowing chutes. If granule segregation is a problem, and it can be to most of us in the roofing industry, it's very possible to redesign or modify handling equipment and storage facilities to prevent segregation in the first place, or to create very effective remixing apparatus. When you're shooting for the highest quality end product, it makes sense to begin with your materials handling. 3M's technical service staff can assist you in solving segregation problems, or introduce you to experts in the field of materials handling for further assistance.